probably most of you meet him. He is the director of REDS Institute and Full Processor and the PI of the ACM MakerSpace project for the Swiss part. And he is going to present some stuff on SDR and machine learning. Alberto?
Yeah, okay. So I was saying, inside the framework of SDR MakerSpace, we tried quite strange path. So we tried to do just open source implementation of machine learning algorithm inside an SDR platform. So we saw a lot about what SDR is. I had this small ML part here, and so I'm not an ML expert, absolutely not. So I'm not teaching machine learning, and but we are curious, and it could be a tool that can provide benefit in some domains. And so we tried, and I would like to try to introduce you why it could be useful in SDR domain, and then how, with open source tools, you can go all the way down to have it running on your platform. So from 1,000 feet fly, what machine learning is for me is just a shifting of paradigm. We actually usually write algorithm. You saw a lot for GPS today, for other communication blocks. Brilliant minds do the math and then implement the algorithm, and then we have a digital signal processing system that just work. This is totally different. We write an algorithm, and then we provide a lot of data to this algorithm. In some ways, curve fitting or something like that, some process inside it, and we come out with a model that is able to do something, classify, predict, or just be a model and be useful in many, many domains. Why now? Because basically, as I already said, we need a lot of data for this algorithm to work pretty well. And okay, with our connected society, this huge amount of data is actually available today. And so it's quite easy to have now an algorithm to look an image and then pass many, many, many filters, kind of filters in this kind of machine learning approach called deep neural networks, and then say, okay, this is guys playing football. And devise an algorithm, a standard digital processing algorithm. To do that is not straightforward. So there are some domains where this kind of algorithm are approaching the accuracy of a human being. So they are interesting. We have security cameras, and we can analyze the stream of images. We can do a lot of interesting things. So once again, very, very broadly, normally a machine learning system has different phases. So you start designing your model, your system. You choose some architecture already available, or you devise your architecture, and then you train it. The training phase is when you provide a lot of data to the system to give the system the opportunity to learn something. And then there's a second phase called inference, when you actually use your training system to do something useful, okay? So let's use the image example. That's probably it's one of the easiest one. You start with a lot of images of nice pets, and then already classified maybe, and then you go through this process. This is a very statistical process, so there are many algorithms to do that. And then you find out what's the right weights that you have to use in your model to be able to classify another image never seen before as a dog, okay, for example. So this is the two. What we are more interested in this kind today in my presentation is the inference part. I won't spend much time in training. There are two completely different type of computations. They require different kind of data. They are very, very two different beasts. And I'll focus more on the trained one because it's when you want to deploy it in your SDR platform. So if you now have a very, very broad idea of what machine learning could be, why machine learning and SDR could be meaningful. But basically because there are a lot of challenges in making communication that could benefit from a machine learning approach. And I just listed some of them without any presumption of completeness or being too specific on any of them. But of course, we can do spectrum sensing, so we can understand what's going on in the electromagnetic spectrum. We can work on dynamic spectrum allocation. We can detect jamming and deploy anti-jamming techniques. Broadly speaking, doing cognitive radio approach of any kind, or also going very, very down to the physical bits. And so imagine to learn the modulation and demodulation scheme from the environment. So this is something that is partially done, or a very interesting direction in research, and having adaptive waveforms and system that can react and actually basically do something that is very hard to describe in a standard algorithm. So if I convinced you in these 5 minutes that could be meaningful, but that's not only positive things about machine learning. And one of the most negative point, from my point of view, is the complexity. So these algorithms are not for free. And this is a fantastic picture where you can see the giga operation per second for classifying just one single image. Okay, image processing is one of the domain where they really, really pushed a lot of research. So we have these fantastic graphics easily to explain. There's much, much less work done in the SDR domain. But just to give you an idea, this is the latest models, very advanced models with a great accuracy in detection, for example, for classification of images. But we have gigabyte of operation per image. If you want to classify them in real time, it's very challenging from the computational point of view. Training is even worse than that. Training is taking data centers, is burning an immense amount of energy, but already inference is kind of a problem. And to give you another view of the same problem, maybe someone here remember this picture. It was a television emission in 2011, Jeopardy. It was the first time that an artificial intelligence called Watson had better result than 2 humans champion. Okay, fantastic, but what was outside of the picture is actually the power consumption. So we had 2 brains and just 1 fantastic data centers, okay? So this is something we have to take in account if you want to really do a fair comparison of where we are right now with this kind of computation. But okay, let's assume we are ready to pay this price, and we really want to go with open source, up, down, and integrate in our system, and that's complex. Why it's complex? So the first step is that you need someone that basically knows one of these frameworks. And this was the famous frameworks yesterday. Maybe today there are 2 new, because it's a domain that is super quickly changing all the time. And in these frameworks, you design your model and you train your model, okay? And the output normally of these frameworks is something that is specific to the framework. And the second phase, so the inference, the deployment on a system, is extremely different if you start from TensorFlow or from another environment. There's a lot of energy today oriented to make some open exchange format for that. And so kind of building an intermediate layer that give you the opportunity to take input from whatever you want to use to design your system and then run it on a common platform. In the activity we've done in the SDR MakerSpace system, we analyzed several of these options, and we selected ONNX as one useful backend that can run your model on several platforms. So when you did that, you still have one open point. So we already see this kind of graph this morning. This is exactly the same. you have a trade-off. So you have a trade-off where you trade flexibility, easy of programming, deployment, and whatever, with energy efficiency. And sometimes using FPGAs or using a specific processor for something, it's order of magnitude more efficient from the energy point of view. But on the other side, it requires probably a lot of engineering effort, and maybe you can, the platform that you use or you build is not so flexible, and so in the future has to be redone. So find out a trade-off for software-defined radio in this spectrum is also complicated, because we use software-defined radio because it's flexible, so we would like to stay there. But if you want to use machine learning model, we would like to be there, so with something super specific. So we tried to figure out where probably is the nice trade-off, and these two central guys are the candidates I'm going to discuss a little bit more later. So what was missing is a classical GNU radio block for running inference. And so what we developed inside the project is an open source bridge between the GNU radio system and then the inference engine provided, in this case specifically by ONNX. So what happened is that now you can acquire, we saw a lot of this board today, but okay, you have some sample receiver from a ref, you bring them to your framework for training your model, and then you have your model. And with this GNU radio block, you can deploy your model and actually use it, okay? I'm not going too much in the details of this block or of the result of this block, that is a classification example, because we will have a demo this evening, and the developer of the blocks will be there, so it's better to discuss with the expert in the domain that I present the results. I'll focus a little bit more on the data rates, because yeah, that's not good news. As you can see, probably being able with a pretty much very modern CPU to handle less than 1 megabyte per second, that's not exactly what we would like to have in a modern software-defined radio platform. If we move to GPUs, it's better. It's definitely better. We go a higher data rate, and especially if we are able to trade the latency. So if we are able to batch more work, GPUs are more efficient. So we transfer a big chunk of data to the GPU, and then we process in parallel to the acquisition of the new data. We reach reasonable data rates, but once again, we are trading latency that is out of the picture, so not in every context we can do that. But the overall accuracy, so that, for example, here is a classification of different modulation, could be quite good. Of course, there are parameters. For example, here we trained it and we tested with variable signal-to-noise ratio. But when you have a decent signal-to-noise ratio, the classification is overall quite promising. The idea is that this block is a tool, is an open source tool, so please go to the GitLab of the project and check it out. And then Kevin and Oscar are here and will be here this evening. Talk to them and they will present you much, much better their work. Actually, if you look from the GNU radio interface, you design your diagram, and then there's a new block, so it's out of the 3 module that you can import, and then you can choose if you want to run on CPU or GPU to do your inference. And at this point, we took another exploration and said, okay, but it could be fantastic if we could go up to the FPGA. Many SDR system has an FPGA, and as we heard just before, it's usually underutilized. It's there, but there's not much processing on that. Can we use the spare gates that we have in the platform to do machine learning inference? Let's see. Probably yes, but the path is not straightforward, and there are many issues. So here is a, once again, incomplete list of the available technologies that can help you in the process. And they support a different set of input and output formats, and exactly as for the design frameworks, they are super quickly evolving. So this was true a few days ago. Maybe someone added an interface just right now. And because more often than not, the interface module between one framework to another is the work of someone that just needed that conversion, and so it's just a GitHub repository somewhere that they don't maintain. Probably it's not evolving with the main framework, and so sometimes it requires some work to do that. Okay, but the idea is that yes, we have some open source tools to do the job. None of them is a push button solution. So none of them can give you the opportunity to take your model, just push a button, and we have the FPGA ready. They need some competence in the dealing with tools, and it's a complex picture because probably the model is written in something like Python, but probably who works on the FPGA knows very well VHDL, Verilog, or something like that. And so there's also a bridged gap in the comprehension and the kind of things that you can do. But basically, it was very hard to determine from this point of view which one of these solutions could work. And so we selected two that was looking very promising when we started the activity and started to do all the way down. And the two approaches I'm presenting here are open source approaches, but there are the two great families of technologies that are today available. One that is represented by this TVA open source project, or also from NVIDIA with the NVLA accelerator, is the idea of providing a bit stream on the FPGA with a specific processor for machine learning. So you don't need to do any design in the FPGA. You just grab the design that they did for us, and you deploy it on the FPGA. And then they provide you quite complex compiler, actually, that takes your model and then do graph optimization, tensor optimization, just-in-time compiler, and mapping on the processor itself, and then produce the interface and all the code running on the processor to do the inference. Okay? And if you take NVLA, it's open source but NVIDIA sponsored system. Otherwise, this is a university approach, a university tool chain that can be used. And it works. We did all the path, and with some effort, you can produce your output. But the idea is the same. You get a fixed processor that is designed by someone with all the expertise in FPGA design, in computer architecture, and it's optimized for this kind of computation, and then you program it with your specific model. Okay, so it's kind of a hybrid trade-off. You are not using gates directly, but you are implementing a processor there, and then you are programming it. The other possibility is to create your own IP, your own gates implementing your model. This is also possible, and this is the approach of this other project that is once again a university project, and gives you the opportunity to do the similar things compared to this kind of processing, but getting a different output. The output that you get from this tool is a C++ design model directly derived from your Python description of your system. Okay? But then what you do with this C++ model? But you use another technology that is called high-level synthesis. That is another option we have today to create FPGA design. Traditionally, we use VHDL, Verilog, or schematic entry to do design. Now, we use something different. We can use C++ or a subset of C++. And many vendors, this is Vivado HLS, but the chain support also different high-level synthesis tools, provides you with a nice small potentially AXI interfaceable IP that you can deploy on your system. So that's probably you can integrate also in the framework we have seen before. Okay, so there's another step there, and then what you get is not, as in the previous technology, directly utilizable for you. You still need to integrate this system with your design or with whatever you have on your final platform. So basically, that's it. I know I've not been in many details because the subject is super huge. I hope that I put you some curiosity to investigate more this stuff. We are happy to answer all your questions or go in the deeper details with you. But the basic idea is that machine learning, it's promising in many domains. Maybe software radio is one, software-defined radio is one of them. But it's computationally intensive, and GPUs are not always available. And especially GPUs are super comfortable if you work with the floating point numbers. But if we work with the other kind of data, fixed point, maybe 12, 14 bits from our ADCs, that's not the best in many, many terms. In that case, we can have FPGA specialized systems, but it's far from being automatic and is a word that is changing so fast that probably tomorrow nothing what I have presented will be still pertinent or still the top of the technology. With that, thank you very much for your attention.
Do we have any questions?
I find interesting when you try to find the modulation or the signaling format. I believe that this improvement that you have at a signal-to-noise ratio has to do with the fact that you're keeping the same signal format. If you, in theory, if you try to work at capacity, as you increase the signal-to-noise ratio, then you have also to change the signaling format. And information theory says that when you are operating very close to capacity, what you receive looks like a Gaussian point. So at that point, I believe there would be little hope anymore to be able to detect the signaling scheme. So if you're operating at capacity, probably that wouldn't work anymore. Is that correct?
That's probably true. What's very complex with this kind of system, or what we realized for us was very complex, is that it's very difficult to relate the performance you get at the output of your machine learning system with the structure of your machine learning system and with the training set that you use for your machine learning system. So maybe some features that are really in the Gaussian domain basically could be that are very special for one modulation compared to another and could be detected, but it's not in the modulation itself. But that's very specific of the training set. So one of the limitations, for example, if you use just one SDR to train your system will be able to detect probably only things with the same SDR. If we take another front end, it will be different. That's why at the beginning I said now it's working and it's everybody is using this because we have huge amount of data. But if you train your neural network with just the photo from your camera, probably I take a photo with my camera, it's not gonna work. So there's a limit, of course.
Yeah, thanks. Very interesting presentation. Just a note, I don't know if you knew about this AirT SDR, which was, I think, a Kickstarter 1 or 2 years ago.
Yeah.
Just checked, it seems to be selling commercially now. I'm curious, where do you see a potential market for machine learning in radio comms? Because it seems that this AirT device, which is an integrated box essentially, which I understood with TensorFlow units, TPUs, and CPU, and an FPGA, and a software-defined radio all in a box. So this product, and it seems to be running well. So, but I'm really curious to see the market there for research, absolutely. But yeah.
Yeah. As far as I can say, right now, all of this is just for research. There's many opportunities, let's say. There's a lot of grand challenge where, for example, for spectrum allocation, you would like to use this kind of algorithm on the fly. But it's just basically research. And so the RT platform, as far as we can say, is a GPU integrated, has an NVIDIA physical GPU integrated right away with FPGA. And one of the benefits is the higher bandwidth that you get. Everything we've done is done with a standard PCI Express GPU. So it's more, you have your front end, you download the data to your working machine and you analyze. So if you need to deploy and learn on the field, that could be a market for this kind of platforms. But I haven't seen any product in the software-defined radio that already use this kind of things. Detection is something that is also classification or detection is something that is a classical application for this sort of things. But probably a coupling of traditional techniques augmented with machine learning capabilities could be a solution, a viable solution for a product. But standalone, there's still a lot of work to do.
So do you have any numbers regarding the power computation to power ratio? What do you get from FPGA, CPU, and GPU?
I haven't my numbers, but there are some numbers in literature. What it seems, and there's no agreement on how to measure these numbers. What I haven't showed here is why the Watson machine was using that much energy compared to the human brain. Okay, compared to human brain, let's say, compared to another system, is that you have a lot of data movement. So everything is in your main memory, that's huge quantity of data, and you have to move back and forth from your computation engine. And GPUs has local memory, and TPUs, that is the Google system, has kind of different technology for memory integrated as well. And so comparison seems not that fair. There's a publication from Google when they came out with the TPU processor with power figure on that. But then it was a rebuttal from NVIDIA saying, no, that's unfair. Our platform is better than what you measured and you declared. So it's really an open discussion. There's a lot of tricks also that you can do on your model. So right now I'm aware of an open source initiative, MLPerf, that is a benchmark as we had, I don't know, benchmark for processor. Now we have a benchmark for machine learning. And that's a set of constraints of the model you have to test. And then the comparison seems a little bit better.
Okay,
But there are order of magnitude of difference.
For your application, the core, the NVDLA core that you used, that, and then probably a GPU.
So there, if you use the FPGA, the big deal is the data precision, how you represent your information. There are some work on binary neural networks. So basically all things in your model is just 1 bit. And that for any kind of GPU, CPU is a nightmare because they have to do mask and shift or just represent with the 32 bits, maybe just 1 bit of information. For FPGAs, it's a piece of cake because just 1 bit, you synthesize 1 bit and it's fantastically fast and energy efficient. So it really depends on about what you want to implement with your system.
So the second project that you presented, if I understood correctly, it was essentially integrating an SDR data, IQ data flow, and feeding it into a neural network model of some kind. So I'm wondering, is there also the possibility to have a feedback to the SDR hardware? For example, that your neural network decides somehow, okay, the gain is too high, you need to lower the gain, or you change the center frequency. Is this currently possible, or would it be possible to implement this, or is it too heterogeneous to have that?
No, it's possible. The interfaces, you can create whatever your model output is, and then actually we give the feedback back to GNU Radio, but you can catch it in hardware and react to the output directly on hardware. That's definitely something you can do.
Okay, one question for me too. In your example, you used the raw IQ from the SDR directly. So many people here will agree that this could be somehow, we can somehow help the machine learning by doing some pre-processing. So for example, let's say for the FS case, if you do the quadrature demodulation, or for a BPS case, you square the signal. For the QPS case, you quadruple the signal and stuff like that. Have you seen if this helps? Because my intuition is that should help, but from any discussion with machine learning guys, especially that are involved with neural networks, they say no, just feed the raw IQ and should be fine.
I'm not expert enough to answer you, but it's true that the network will discover things. And maybe what you are thinking is an help to the system. Actually, is not, because you are filtering or cancelling some feature that the network detected as important. On the other hand, if you look at the computation, that could be very interesting, because if you have a low-cost technique to split your IQ data in two categories, where you are sure that the information is in these two categories, you can train a much smaller network then to detect things. So that could be possible.
And do parallel.
And you do parallel inference, definitely, yes. But you can have n model in parallel, and then split your input, or send the same input at all models, and they will detect different things. So, or one huge model that have all the knowledge. It's
Okay.
all possible.
So we are thinking we are good.
Thank you very much. So we can proceed with another coffee break. As usual, upstairs.